Section 6.4 is concerned with the topic of the electronic structure of atoms. What we mean by this is that we want to learn how to write the location of every electron in an atom in a manner that is consistent with the Schrödinger equation. That is, we identify the important quantum numbers of every single electron in an atom. Now, we're going to be using a shorthand notation to do this rather than the actual quantum numbers themselves. And we're also going to use something called the orbital diagram to help explain how electrons are spinning. So when we build up the electron configuration of a multi-electron atom, we're going to use the Aufbau principle. And what this really means is that we're going to begin by putting electrons in the lowest lying orbital, the one that is closest to the nucleus, and working our way to higher energy orbitals systematically. So Aufbau is just a German word that means construction, and this was just the terminology that was used by Niels Bohr when he began developing this system. So it turns out that for the hydrogen atom, the energy levels depend only on the value of the principal quantum number n. That is, that the different subshells within a shell don't affect the energy of the electron. And that's why the Bohr equation works with just the one quantum number n in there. However, as soon as we put more than one electron into our atom or ion, the situation becomes more complex, and the different subshells that make up a shell are no longer equivalent in energy. So, if we look at a given shell, that is a set of orbitals that all have the same n value, we'll see that the subshells within that shell, that is the S, P, D, and F subshells, fill in the order S, P, D, and F. Now, there is a slight problem. If you recall when we were talking about the Bohr model of the atom, we said as we go to higher shells, the shells get closer and closer together. And then as we split our shells out into different subshells, we start getting some overlap. And the first obvious indication of this is the order of subshells with respect to the 4s and the 3d. You can see there that it doesn't follow the expected pattern. Okay, so we're going to need to keep that in mind. Now, it's worth at this point recapping the Pauli exclusion principle. And the Pauli exclusion principle states that no two electrons in the same atom may have the same set of quantum numbers. And so what this means is that if two electrons have N, L, and Ml in common, then Ms must be different. Or another way of saying that is that two electrons in the same orbital must have different spin. So, an alternative statement of the Pauli exclusion principle is this: only electrons with opposite spins may occupy the same orbital. So, here we have a p subshell, which is comprised of 3 orbitals, and you can see here in each orbital we have opposed spins. So this is a valid arrangement of electrons. In the lower case, we can see that we have one of our orbitals with 2 electrons with the same spin. Those 2 electrons would have all 4 quantum numbers the same. So this is an invalid arrangement of electrons. So that's it. If 2 electrons are in the same orbital, they have opposite spins. Now, a little bit of convention here. We normally put the first electron that goes into an orbital in with what we call spin up, and then the second one will go in spin down. That's just the convention we have. We indicate the spin of an electron with a half-headed arrow because the spin quantum number is either plus a half or minus a half, and that just reiterates that point. So, when we have multiple orbitals making up a subshell, then they will have the same energy. We say that those orbitals are degenerate. If this is the case, how do we decide where to put the electrons? Well, this was figured out by a guy called Hun, and he came up with what is now known as Hun's rule. And that says this. It says electrons will not join electrons in the same orbital if an unoccupied orbital is available. So it's kind of like seats on the bus, right? You're not going to sit next to a stranger if there is a seat available where you could sit alone. However, once every seat is singly occupied, well, then people start doubling up on where they are sitting. Or you can think about it like bedrooms in a house. If a family has a 3-bedroom house, 2 parents and 2 children, everybody gets their own bedroom. As soon as the 3rd child comes along, well, they have to share with a sibling. So you get the idea that the electrons really don't want to be in the same region of space because they will repel one another. They're both negatively charged. So if they can, they occupy an orbital alone. So let's have a look at this. Here's a p subshell again. A p subshell has 3 values for ml. So 3 possible orientations, all with the same energy. So p subshell is made up of 3 orbitals that are degenerate. And if I wanted to put 3 electrons into a p subshell, the correct way of doing it would be to put 1, 2, 3 in each orbital rather than doubling up and then leaving 1 vacant. Okay, that would be the incorrect way of putting 3 electrons into a p subshell. Okay, so what we're going to do is we're going to work through the electron configuration for the first 3 rows of the periodic table. Now, the first row of the periodic table is pretty easy because there's only a couple of elements in there. So the first thing that you want to figure out is how many electrons does your atom need? And the number of electrons in a neutral atom is simply equal to the atomic number. So hydrogen, because it has atomic number 1, it has 1 electron, and that's going to go into the 1s subshell. So we would write its electron configuration like this. The 1 here indicates the shell. The S indicates the subshell. And the 1 as a superscript there is the number of electrons. Okay, so that all together is what we call the electron configuration. Over here, what we've got is an orbital diagram where we draw a box which represents the orbital that contains the electron, and then we put 1 half-headed arrow in there directed up to indicate the 1 electron that is in that orbital. And we always label our orbitals. So this is called an electron configuration, this is called an orbital diagram, and you need to know how to construct both. Our next element in period 1 is helium, and it has atomic number 2, so therefore it has 2 electrons. So this will fill up the 1s orbital. So there's the shell, there's the subshell, and the 2 indicates that we've got 2 electrons. Here's the orbital diagram showing both of the electrons in the 1s subshell, and you can see that they have opposed spins. Okay, so now we're on to period 2, and if you're sharp, you'll realize that we've filled up the 1s subshell, so we'll need to move on to the next subshell. So period 2 is composed of lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So we have a total of 8 elements here. lithium has atomic number 3, so that means it has 3 electrons. The first two go into the 1s subshell, and then the third one goes into the 2s subshell. Instead of writing out the electron configuration using the subshell notation, we can also write out the orbital diagram, and you can see that lithium has one unpaired electron in the 2s subshell by itself. So, lithium has electron configuration 1s2, 2s1. Now, if you were sharp, you'll remember that 1s2 is the electron configuration for helium. So what we could do is condense the electron configuration of lithium and write it like this. We're going to put the symbol for helium in square brackets, followed by 2s1. So this achieves a couple of things, but most importantly for lithium, what it achieves is it makes it clear that the 2s1 electrons, the ones that are on the outer edge of the atom, are focused on, right? That focuses our attention on those outer electrons. The electrons are in the outermost orbitals. These inner electrons that are in the helium configuration, they're referred to as core electrons. And the atoms cannot interact with one another through their core electrons. They always interact through their electrons that are on the outermost surface. So these guys are not involved in bonding. So they're less interesting to us. The electrons that are on the outer edge of the atom, the 2s1 electron in this case, the ones that are in the outermost orbitals, they're referred to as valence electrons, and they're the ones that are important for chemical reactions and for chemical bonding because they're on the outer edge of the atom. So now let's move on to beryllium. Beryllium has atomic number 4, so therefore it has 4 electrons. So the full electron configuration would be 1s2, 2s2, and then that completely fills the 2s subshell, so we'll need to start the next subshell after beryllium. Of course, we can replace 1s2 with the symbol for helium in square brackets, and that would give us the abbreviated or condensed electron configuration for beryllium. Boron has atomic number 5, so it has 5 electrons, and as I mentioned, we're going to need to start the next subshell, which will be the 2p subshell. Now, it's important to recognize that a p subshell has 3 orbitals because the ml values can be -1, 0, and +1 when L equals 1. Okay, so you can see you can fit 6 electrons into a 2p subshell. Again, if we want to, we can replace 1s2 with the symbol for helium in square brackets, and that gives us the condensed or abbreviated electron configuration. These are the valence electrons, or the outermost electrons, the ones that would be involved in bonding for boron, the ones on the outer edge of the atom. Okay, so as we move further across period 2, it's going to get quite boring because we're going to be filling up this 2p subshell here, aren't we, right? Steadily filling that up. So carbon has 6 electrons because it has atomic number 6. So we've got 1s2, 2s2, 2p2. And of course, again, we can replace the core electrons with the symbol of helium in square brackets to give the condensed electron configuration. Note that we put the second electron that goes into the 2p subshell into its own orbital. Moving on to nitrogen. Nitrogen has atomic number 7, so it has 7 electrons. So we're going to add a third electron to the 2p subshell. And again, this is going to go into its own orbital spin up. We can write the abbreviated electron configuration by replacing the core electrons for the symbol of helium in square brackets. So we would say that nitrogen has 5 valence electrons. Moving on to oxygen. Oxygen has atomic number 8, so we've got 8 electrons, and we're going to add that electron to the 2p subshell. Note how we now start doubling up, but that fourth electron that goes into the 2p subshell goes in spin down, because if we do have 2 electrons in an orbital, they have to have opposed spins. Moving on to fluorine, we have to squeeze in 9 electrons, so we're going to add another electron to the 2p subshell, and again, that one's going to go in spin down because we're doubling up in a second 2p orbital. Now we're on to neon, and so we add another electron to the 2p subshell because neon has 10 electrons. These guys are the core electrons, and these ones here are the valence electrons. So the 6th electron goes in spin down in our third orbital in the 2p subshell, and that completes the 2p subshell, and now we need to move on to the next subshell as we start period 3. So period 3 is comprised of these elements: sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. 8 elements again. Sodium has 11 electrons, and so the 11th electron begins a 3s subshell. Note when we abbreviate this, what we do is we write the symbol for the preceding noble gas in square brackets, followed by the number of outer electrons. So the preceding noble gas was neon, which has that electron configuration. So that takes into account the 10 core electrons. Magnesium has 12 electrons, so that completes the 3s subshell because an s subshell can contain at most 2 electrons. Okay, so now we need to move on to the 3p subshell as we begin to fill up from magnesium onwards. So aluminum has 13 electrons, and that final electron is going to go into a 3p subshell. Again, we can replace the electrons that are the core electrons with the symbol of the preceding noble gas, neon, in square brackets. So aluminum has 3 valence electrons. That's the valence electron configuration for aluminum. Silicon is element number 14, so for that reason it has 14 electrons. We're going to add the 14th electron to the 3p subshell. Remember, we can put up to 6 electrons into the 3p subshell. And we can also abbreviate the electron configuration by replacing the core electrons with the symbol of the preceding noble gas, which is neon, in square brackets, and then following that up with the valence electrons. So silicon there with 4 valence electrons. Phosphorus, atomic number 15. So we put that into the 3p subshell. So at this point, if we think about the 3p subshell, every orbital would be singly occupied. And as we move on to the next element, we're going to start doubling up. we can abbreviate the electron configuration of phosphorus by writing the core electrons as the element of the preceding noble gas in square brackets, followed by the number of and arrangement of valence electrons. So phosphorus has 5 valence electrons. Sulfur has 16 electrons, so we're going to add an extra electron to the 3p, giving us 3p4, but now we have to start doubling up, and we need to make certain that that fourth electron goes in spin down, because we can't have 2 electrons with the same spin in the same orbital. Again, we can abbreviate by substituting the core electrons with the symbol of the preceding noble gas in square brackets, followed by the number of valence electrons. So sulfur has 6 valence electrons in the configuration 3s2, 3p4. Chlorine has 17 electrons, so we add another electron to the 3p subshell, and again we can abbreviate the electron configuration by writing the core electrons as the symbol of the preceding noble gas in square brackets. Argon completes row 3 of the periodic table, period 3, and argon has 18 electrons, and that finishes off the 3p subshell. Again, we can abbreviate the electron configuration of argon. Note that we don't write argon by itself in square brackets. We always write the symbol for the preceding noble gas in square brackets, followed by the number of valence electrons. Okay, so now we move on to the 4th row of the periodic table, and the question becomes, what comes after the 3p subshell? So beyond the 3p subshell, the orbitals do not fill in an obvious way. In particular, we might expect that the 3d comes after the 3p, but it doesn't. It's 4s that comes after the 3p. So we're going to go 1s2, 2s2, 2p6, 3s2, 3p6, and then we start filling up the 4s. And like I said, that's not obvious. You might have expected that it was going to be 3d. So how do we remember the correct order of subshell filling? Well, what we're going to use is what's called the Aufbau diagram. So we write 1s down to 7s in our first column, 2p down to 7p in our second column, 3d down to 6d in our third column, and then 4f down to 5f in our fourth column. And then we draw these diagonal arrows in, and this gives us the order of the subshell. So it goes 1s, 2s. When you get to the end of an arrow, you loop back and start the next arrow. So after 2s is going to become 2p, then 3s, and then 3p, then 4s, and then we come back, and then we do 3d, 4p, 5s, and we come around 4d, 5p, 6s, 4f, 5d, 6p, 7s, etc. Okay, we have one more row we might do. So you will need to know how to draw the Aufbau diagram and also use it to get the correct order of subshells. So in the 4th period, we're going to begin by filling up the 4s subshell. So that's one orbital in the 4s subshell. And then we're going to move on to the orbitals that are in the 3d subshell. So potassium has the argon configuration for its core, and then we put in 1 electron into the 4s subshell. Calcium has 18 electrons in an argon configuration, and then it has a completely filled 4s subshell. Now we've filled the 4s subshell, the next subshell is going to be the 3D, and we're going to be filling that for quite a while because D subshells hold 10 electrons. So just remember, S subshells have a max of 2 electrons, P have a max of 10 electrons, no, 6 electrons, D have a max of 10 electrons, and F have a max of 14 electrons. So we move on to scandium. We put an electron into the 3D subshell for the first time. Titanium, we add another electron to the 3D. Vanadium, we add a third electron to the 3D. Now chromium, you might expect that it would be argon 4s2 3d4, but there's actually an exception to the rule. We steal an electron from the 4s and we put it into the 3d. So there's an exception there for chromium, which is why I highlighted it in blue. Okay, for manganese, it continues with the expected pattern. We add a 5th electron to the 3d. Iron continues the expected pattern. We add a 6th electron to the 3d. Cobalt, we add a 7th electron. Nickel, 8. And for copper, we might have expected, if it was following the predictable pattern, that it would be 4s2 3d9, but the same thing happens as what happened for chromium, and an electron from the 4s moves over to the 3d to give 3d10 4s1. And then zinc finishes off the 3d subshell and has outer electron configuration 4s2 3d10. Now, once we finish the 3d10, then the next subshell, according to our Aufbau diagram, will be the 4p. Okay, so something we want to be mindful of as we're filling up 3D is that there are 2 exceptions, one for chromium and one for copper. This gives us an electron configuration for chromium that ends in 3d5 and an electron configuration for copper that ends in 3d10. And the reason for this is because a half full or completely full D subshell is very stable. So it's not quite as stable as a noble gas configuration, but it's very stable. So by taking an electron from the 4s and putting it into the 3D, chromium gets a much more stable electron configuration. Similarly with copper, by taking an electron from the 4s and putting it into the 3D, we can see that should say 3d10, shouldn't it? We can see that copper gets a completely filled 3D subshell, which is especially stable. Okay, once the 3D orbitals are filled up, we then move on according to the Aufbau diagram to the 3p. So to the 4p. Gosh, lots of typos in this one, isn't there? 2 typos on the one slide. And so we can put a total of 6 electrons into the 4p, and that gets us all the way through to krypton. The 5th row of the periodic table follows the same patterns as what we saw in the 4th row of the periodic table, but there tend to be a few more exceptions, which we're not going to get bogged down in. When we move into rows 6 and 7, we start getting into elements that have F subshells for the first time. So these elements at the bottom here the inner transition elements, or sometimes they're referred to as the lanthanides and actinides, these guys all have electrons in F subshells. So I'll give you an example of this. If we look at hafnium, here we are here, element number 72, we're going to see that it has, because it comes after lutetium, 14 electrons in an F subshell. Okay. If we look at other elements that are in rows 6 and 7, say for example mercury here in row 6, we see the same thing. It has 14 electrons in an F subshell. Okay, here's thallium. So thallium is element 81 in row 6. And again, we see that thallium has 14 electrons in an F subshell because thallium comes after lutetium. Okay. All right. So you'll notice, if you pay attention, every time we get to a noble gas, we completely fill a P subshell. So all of the noble gases have a completely full P subshell with 6 electrons in it. And that's worth noting. Okay. Period 7 is similar to period 6. We see F electrons, and this time they're going to be 5 F electrons that we're filling up. If you look at the periodic table, you can see a general pattern. In the first row, we're filling up a 1s subshell. In the second row, we're filling up a 2s and a 2p subshell. In the third row, we're filling up a 3s and 3p subshell. In the fourth row, we're filling up a 4s, a 3d, and a 4p subshell. In the fifth row, we're filling up a 5s, a 4d, and a 5p subshell. And in the sixth row, we start seeing F electrons for the first time. We're filling up a 6s, a 5d, a 4f, a 5d, and 6p subshell. And in the seventh row, we're filling up a 7s, a 6d, a 5f, and that's it. That's all we, and I should say, and a 6d subshell. I guess 6d appears twice in this diagram, doesn't it? All right, so what you can see is all of the elements over here, their last electron will be going into a p subshell. All of the elements that are over here, their last electron will be going into an s subshell. Those elements that are in the middle, their last electron will be going into a d subshell. And for those elements that are in the inner transition elements below the periodic table, their last electron will be going into an F subshell. So, what about ions? Well, ions form when atoms lose or gain electrons. So if we want to write the electron configuration of a cation, of one of those elements that's in what we call the S block, so just going back for a moment, these first two columns here are referred to as the S block. These guys are referred to as the P block. These guys are referred to as the D block. And these ones the F block. Should have mentioned that. Okay. So if we want to write the electron configuration of a cation for an S block metal, that is a metal that's in row 1 or group 1A or 2A of the periodic table, what we're going to do is we're going to begin with the electron configuration of the neutral atom. So sodium has 11 electrons. 10 of the electrons are core electrons in the neon electron configuration, and the 11th electron is in a 3s subshell. So to get the electron configuration of a cation, what we have to do is take the electron configuration of the neutral atom and remove electrons equal to the size of the positive charge. So say we want to write the electron configuration for the sodium ion, which has a +1 positive charge. We have to take away 1 electron. So we're going to take away the 3s electrons. So what we're left with is the neon core of 10 electrons, 1s2, 2s2, 2p6. To write the electron configuration of an anion, and anions are formed by non-metals, which are those elements that are in the p block. What we're going to do is we're going to begin with the electron configuration of the neutral atom. So for example, for fluorine, which has 9 electrons, this would be the abbreviated electron configuration for fluorine. We have 2 core electrons in the helium configuration, and then we have a total of 7 valence electrons filling up a 2s subshell, and then 5 electrons in the 2p subshell. So to write the electron configuration of the anion, we have to add electrons, because electrons are negatively charged, equal to the size of the negative charge, and we're going to put those into any partially filled orbitals. So fluorine forms a 1- anion. So we're going to add an electron to the partially filled 2p subshell, just the 1 electron, and that'll give us 2p6. Now, if you remember, 2 electrons plus 8 electrons gives us 10 electrons. So these guys are in the neon configuration. If I can write it correctly, 1s2, 2s2, 2p6. So what you can see is whether an S block metal is forming a cation or a P block non-metal is forming an anion, we always end up with a noble gas configuration, which is kind of cool, and we learnt that in Chemistry 161. So let's just summarize. When the main group elements, those are those that are in the A groups, that's what we mean by main group, the A groups, when they form ions, they become isoelectronic, which means having the same electron configuration as their nearest noble gas. So lithium loves to lose 1 electron, giving it the same electron configuration as helium. Sodium loves to lose 1 electron, giving it the same electron configuration as neon. Calcium likes to lose 2 electrons, giving it the same electron configuration as argon. Fluorine loves to gain 1 electron, giving it the same electron configuration as neon. Oxygen loves to gain 2 electrons, that should be a 6 there, giving it the same electron configuration as neon. So we've looked at how we write cations of the S block metals, anions of the P block nonmetals, but what about the cations formed by the transition elements, or what we call the D block metals? Well, what you want to do is, again, begin with the electron configuration for the neutral atom, which we know how to write using our Aufbau diagram. And then we're going to remove electrons equal to the positive charge, but from the orbital that has the highest shell number, the highest principal quantum number. So in this case, that would be 4. So if we want to write the electron configuration for iron 2+, we're going to get rid of the two 4s electrons. So we're going to remove the s electrons before we remove the d electrons. Now, only if the ion has a charge greater than +2 will we need to remove some of the d electrons. So for example, if I wanted to write the electron configuration for iron 3+, first I would remove the two s electrons because they have higher shell number, and then I would take away one of the d electrons. Say I want to write the electron configuration for scandium 3+, well then it's kind of a no-brainer. I have to take away all 3 of the valence electrons. If I want to write the electron configuration for silver plus, I have to remove electrons from the valence shell that has the highest number. So I'm going to take electrons from the 5s subshell here, and that'd give me electron configuration krypton 4d10. Okay, so again, we're only going to be removing any of the d electrons when the charge on our transition element is greater than +2. So typical problems will be asking you to write the electron configuration for a particular element or ion. So if I was asked to write the electron configuration for titanium 4+, what I would do would be to write the electron configuration for titanium, and then I would remove 4 electrons, okay? Similarly, for phosphorus, what I would do is I would write the full electron configuration, or for phosphorus 3-, I would write the full electron configuration for phosphorus, but then I would add 3 electrons. Okay, so for titanium 4+, we removed 4 electrons. For manganese 2+, what I would do is I would write the full electron configuration for manganese, and then I would remove 2 electrons. And similarly for copper 2+, I would write the full electron configuration for copper, and then I would take away 2 electrons. Okay? You always want to pay attention to whether you're asked to write the full electron configuration or the abbreviated electron configuration, because you don't want to get that incorrect and lose like some of your points. Okay, so that concludes the video on writing the electronic structure or electron configuration of atoms and ions.